Hello dear GATE aspirants, welcome to VEDA GATE Academy. In the previous discussion, we have done with many things, Laplace transforms, inverse Laplace transforms of basic signals, time shifting, frequency shifting, not only that, initial value theorem, final value theorem in time domain and frequency domain, limitations of initial and final value theorems in frequency domain. In time domain, we do not have any limitation, directly we can apply. We saw these things. And we saw some just introduction of proper, improper and strictly proper functions. Let us go for proper, improper and strictly proper functions. The heading is, come on, heading is proper function. Yes, proper function. Yes, if I take a function in S domain, suppose if f of s is my function, yes, s square plus 2s plus 1 by s plus 1 into s plus 2. Yes, observe it. If you simplify the denominator also, s square plus 2s plus 1 means I will not take s square plus 2s plus 1. Why? Because s plus 1 is getting cancelled. I should not take the things which are getting cancelled, please. The things which are getting cancelled I should not take. Yeah, let's write another what you call s square plus 6s plus 7. Let us take 6s plus 7. S square plus, come on ma, what we have to take? 6s plus 7. Whatever the function you can take, but we should not take a which is going to get cancelled. If cancel also, nothing is going to happen, but order will decrease. Yes, what is the denominator? S square plus 3s plus 2. Observe here. Yeah, before we define what is proper function, denominator degree, we will be taking it as m. Denominator degree. See, denominator degree. Let's take it as m. Numerator degree. Let's take it as n. Okay, n for numerator, m for denominator. Now, what does it mean by degree? Highest power of s. In fact, we will call that one as order. We will define the order. In the upcoming sessions. Okay, we will define the order. But for time being, you remember the highest power of s is called as order. The highest power of s, either in denominator or numerator, is called as order. Okay, what is the highest power of s in the numerator? 2. In the denominator, 2. If the denominator order and the numerator order both are exactly equal, I can write if m is equal to n. If m is equal to n, then that function is said to be yes, proper function. Said to be what ma? Said to be proper function. Means both must have same order. That is about proper function. Let us see what is strictly proper function. Yes, this is very important for us. Yes, strictly proper function. Yeah, it is very useful for us in the upcoming classes. In state space analysis, we will be discussing again about strictly proper functions. There we are going to define some matrices like A, B, C, D. One matrix is going to be 0 there for strictly proper functions. At that point of time, again we will be recollecting. Okay, even in the starting classes itself, we are going to be use this one randomly. Yes, come on here, strictly proper function. What does it mean by strictly proper function? Strictly proper function means if m is greater than n, the order of denominator is more than numerator, it is called as strictly proper function. What is one example for that? One example is some function f of s is equal to s plus 1 by s square plus 5s plus 6. Yes, it is strictly proper function. What is m? M is equal to 2. What is n? N is equal to 1. M is greater than n. This is strictly proper function. Let us see improper function. By this time, you might understood what is improper function. Very simple definitions what we learned in intermediate or in BTech first year mathematics. Okay, improper function. Yes, come on. Improper function. Yes, you can give the answer. Come on, brother, you have to give the answer. Very simple. If m is less than n, one example please, one example. F of s is equal to s square plus 5s plus 6 by s plus 1. What is m here ma? 1, s power 1. What is n here ma? 2, s power 2. Yes, m is less than n. Improper function. Improper function. In the previous discussion, we understood one point that initial value theorem in S domain is not applicable for improper functions. We saw improper functions means improper function means this numerator degree is going to be more, or order is going to be more when compared to denominator order. So these are the limitations of initial and final value theorems. With this, we are done with the limitations. Let us solve one problem of our previous gate on initial and final value theorems. One question is given. The question is given like this. Example question, previous gate question please. Laplace transform of f of t, where f of t is a signal. Yeah, f of t is a signal. Yes, is equal to 2 into s plus 1 by s square plus s plus 5, s square plus s plus 5. Yes, s square plus 2s plus 5 is 2s plus 5. This is the function given. He is asking us to find initial and final values of f of t. Find, the question is like this, find f of 0 plus and f of infinity, f of 0 plus and f of infinity. 0 plus and 0 and 0 minus, the magnitude is all three are same. See, there is no difference in the value between 0 plus, 0 minus and 0. But operation wise, there is a lot of difference between 0 plus, 0 minus, so 0 minus, 0 plus and 0. Only impulse signal, impulse input can give the values of difference, can give different values for 0 minus, 0 plus and 0. Except for impulse, for any signal, the magnitude of 0 minus, 0 plus and 0, all three are same. We discussed already these points. So come on, how to find? Yes, solve it please. Very simple, solve it. Yes, you want what? First of all, look at it. What are the limitations of application of initial and final value theorems in S domain? Final value theorem is not applicable if the given function denominator is having any poles on imaginary axis or any real part in right half of S plane. Right half of S plane. I should not speak poles. The roots of the denominator equation. Why? Because we are not yet entered into poles concept. Simply, I will repeat the statement once again. The final value theorem in S domain is not applicable if the given function denominator roots are having any positive value. Any one is enough for the violation of the rule. Okay, or any of its roots existing on imaginary axis. Now, if you solve s square plus 2s plus 5 for its roots, none of its root is going to have positive real part, or none of its root is there on imaginary axis. Its roots may be complex, we don't know, but root should not exist on imaginary axis. Imaginary axis means what? A real part should not be 0. Okay, now therefore final value theorem in S domain is applicable or not applicable? Applicable. I can apply directly. So f of infinity is equal to limit s tends to 0 s into f of s. What is that? 2s plus 2 by s square plus 2s plus 5. S square plus 2s plus 5. Observe it. If you simplify, the answer what we are going to get here is 0. 0 into anything is what? 0 into anything is what? 0. Observe. 2s square plus 2s, s square plus 2s plus 5. If I substitute 0, 0 by anything is what? 0. Therefore, final value is 0. Yes. Now, what is the initial value f of infinity? Sorry, not f of infinity, f of 0, please. Initial value is f of 0 plus. How to find? Limit s tends to infinity, s into again the same function. What is that? 2s plus 2 by s square plus 2s plus 5. Some people, what they will do is they will directly substitute s is equal to infinity in this expression. They will get wrong answer. We should not substitute s is equal to infinity in the given expression. Please do remember, if you are getting infinite by infinite form, we should not substitute s is equal to infinity. Then what to do? Take the highest power of s and the highest power of s in the numerator and denominator. First you cancel those. After that we can substitute what? S is equal to infinity. This is the concept what you learned in mathematics in childhood. Yes, while applying limits concepts. Come on here. What is the initial value f of 0 plus is equal to, what is the highest power of s that we can get common in numerator? S square. Limit s tends to 0. If I take s square, if I take common, s square if I take common, what I'm going to get? 2 plus 2 by s. 2 plus 2 by s. Yes, what is this one? 2s square plus 2s. 2s square plus 2s. If I take s square common, how much I'm left with? 2 plus 2 by s by s square in the denominator also. How much are going to get? 1 plus 2 by s plus s 5 by s square. So this gone. Yeah, both are gone. See, look at it carefully. That is equal to, look at the simplification. Is there any mistake in the simplification? Check it once. I think it is, yes sir, s into 2s square plus 2s we are going to get. If I take s square common, 2 plus 2 by s, perfect. In the denominator, if I take s square common, 1 plus 2 by s plus 5 by s square, perfect. Put s is equal to, not 0 please, infinity, because initial value theorem we are applying, not the final value theorem. Initial value theorem means in S domain it should be infinity. If you substitute infinity, how much are you going to get? 2 plus 0. Because 2 by infinity is what? 0. 1 plus 0 plus 0. How much it is? 2. Answer is what? 2. So this question has been asked in GATE 1995 EC paper for 1 mark. So this much simple it is. Answer is what? 0, 2. Final value is 0. Initial value is 2. I can apply. See, sir, initial value limitation we didn't check. What is the limitation of initial value? The initial value theorem is not applicable if the given function is improper. If you look at the function what we got, it is a proper or improper or strictly proper. It is a proper function. Why? Because numerator order is 2, denominator order is also 2. We can apply directly what? Initial value theorem. The answer what we got is 0, 2. This is about application of initial and final value theorems. So these are very important. We are learning basics very slowly and in depth, so that in upcoming sessions we can directly apply all these techniques without any hesitation. Means we won't think twice before we apply these techniques if we have strong foundation here. That is our aim. Now let us see one more question, Laplace transform question. This question is given in ESC paper, Indian Engineering Services paper. I am expecting answer from you boss, all of you. Please solve this question and give me the answer. Find Laplace transform of t square minus 2t into u of t minus 1. Yes, he's asking about what is the Laplace transform of the given expression f of t. What is f of t given? T square minus 2t into u of t minus 1. Now, if you look at it, unit step function is having a shifting of 1 to the right side, or delay I can call. U of t minus 1 is delayed by 1 unit when compared to u of t. Now he is asking about to find Laplace transform. This is okay having shifting, but this t square minus 2t is not having shifting. I told you we can apply the what you call the shifting techniques, what we learned. If all t terms are having same shifting. See, I told you in time domain all t must have the same amount of shifting. In frequency domain all s terms must have the same amount of shifting. Then only we can apply shifting theorem. Otherwise, it is going to be lengthy if you solve. See, what is the general way of finding Laplace transform? Integral minus infinity to plus infinity f of t e power minus st dt. If you do that, it will take 1 hour for you. Okay. See, please don't do such type of mistakes in exam. And inverse Laplace, if you do 1 by 2 pi j integral of sigma minus j infinity to sigma plus j infinity f of s into e power plus st ds, if you do, it will take 1 year for you to get the answer. Never you commit such type of mistakes. Do not apply formula. Yes, do not apply formula. We have some properties, we have some techniques. You must learn those techniques. Sir, some people they will ask me, sir, I apply only formula. Then I can say one thing for you, that you are not fit for competitive examinations if you apply formula. See, formula can be applicable if the example is very simple example, or if you are not having a direct technique. See, formula you can apply if you do not have any theorem or direct technique. If direct technique or theorem is available for us, never we go for formula application. Here, what the point I want to tell you here is, if you want the answer, first of all, arrange this one in perfect shifting format. What is perfect shifting format, brother? All t terms must have the same amount of shifting. Here we have u of t minus 1. Very simply, we know a minus b whole square formula. Here, let me write this one as t minus 1 whole square. Yes. If I take t minus 1 whole square, what we have? T square matched minus 2t matched plus 1 is extra. Remove that, what you take an extra into u of t minus 1 into u of t minus 1. Then split it. L Laplace transform of t minus 1 whole square into, come on brother, you must answer, u of t minus 1 minus u of t minus 1 minus u of t minus 1. Now apply Laplace individually. Laplace transform of t minus 1 whole square into u of t minus 1 minus Laplace transform of what ma? U of t minus 1. Now why we did like this? If you observe here, this signal is also having shifting, this is also having shifting, both are having same shifting. Here only one signal is having shifting. Therefore now I can apply time shifting property here. Now how to get answer within one step by using time shifting property? Observe here, brother. Yes, observe here. Come on. See, I told you, if you find shifting, forget about it, or you write it in the initial stage itself. I have t minus 1, t minus 1. In time domain, if there is shifting in frequency domain, what we are going to get? Come on, brother. We are going to get exponential in frequency domain with same sign or different sign? With same sign. So because of that shifting, we are getting e power minus s here. E power minus s. Now forget about 1. Why? Because we already wrote it. Then what is the signal? T square into u of t. What is the Laplace transform of t square into u of t? 2 factorial by s cube. That is equal to what ma? 2 factorial by s cube. Yes, the first part is done. What is the second part? U of t minus 1. What is our signal? U of t. What is the Laplace of u of t? 1 by s. Laplace transform of u of t is what? 1 by s. As I have minus 1 here, what is the Laplace I am going to get? Time shifting, e power minus s. E power minus s. This question is given for 1 mark in Indian Engineering Services examination recently. I think in 2018, for 1 mark this question is given. Very simple. We should not spend this much amount of time in examination. As we are at the learning stage, these many steps we taken. Otherwise, one step is enough to get the answer for this question. So with this, we are done with mostly Laplace transforms. Like I will revise once what we discussed: impulse signal, step, ramp, parabolic. After that, sinusoidal, different sketches or graphs of exponential, and with exponential we got in time domain exponential will give frequency domain shifting with opposite sign we saw. After that, time shifting we saw, the proper way of time shifting, frequency shifting we saw, and we saw many inverse Laplace transforms just within 1 or 2 steps. Okay, and after that we went for initial and final value theorems. And we saw about differentiation property and integration property. We saw differentiation property with initial condition, but I didn't explain you about integration property with initial condition. When an example comes, at that point of time, I'm going to introduce you about integration property with initial conditions. But for time being, you try it. If you are not getting, you can ask me. Please, you on your own, you try. If I apply integration property, Laplace to the integration property in time domain to convert into frequency domain, which is having initial condition, what is the formula? You try it. If you are not getting, please you can ask me. Okay, but whenever time comes with an example, I'll be explaining that. Otherwise, if I give that one now, a little bit it is confused to you. That's why we will be explaining it later by taking an example. Meanwhile, you can try now here. The time here now to enter into the representation of RLC elements in time domain and frequency domain. Anyhow, you know how to represent inductance, resistance, and capacitance in time domain, but how to convert into S domain? I told you S domain is having some advantages compared to time domain. Now this is the time to verify, to prove what are the advantages we are going to get in S domain. Yes, but before that, let's get into the topic, that is representation of RLC elements in time domain and frequency domain. Here our heading is representation of RLC elements in time domain. You know about time domain and frequency domain. And what ma? Frequency domain. Yes, frequency domain. Frequency domain, I will write it as FD. Time domain, I will write it as a T dot B shortcut. Okay, time domain and frequency domain. Let us take the first one is a resistor or resistance time domain. Here, let me take here element. Here we'll be taking element. Here time domain. Yes, here it is frequency domain. This representation is very important. Here I'm taking the first element as resistor or resistance. Resistance. Yes, how it is represented with this symbol, you know very well. With this symbol, yes, you know it very well. Now represent in time domain. Yes, what are the units of R? Ohms. Units of R are what? Ohms. If I apply a voltage of V of t across this resistance, then definitely some current I of t will be driven in this. Now, what is the relationship between voltage and current with respect to resistance? So I can write I of t is equal to V of t by resistance, or V of t is equal to what, ma? R into I of t. Yes, this is in what domain, ma? Time domain. Let's come to frequency domain. In frequency domain, also the resistance will be represented with a symbol resistance only. Apply Laplace transform to this one. What we are going to get? If you apply Laplace transform, come on, brother. Resistance, it is going to be very easy. V of t will become what? V of s. V of t will become what? V of s. I of t will become I of s. R will be R only. V of s is equal to R into I of s, or I of s is equal to V of s by R. Means Ohm's law in S domain will be looking like this. V of s is equal to R into I of s. Yeah, V of t, V of s, I of t, I of s. Now, how to write here R in? Let us see the units. This voltage is what? V of s. Then what is the current that is flowing? I of s. If these units are volts, if these units are amps, then definitely resistance units are ohms. Now the first point that we have to understand here is resistance units in S domain and time domain ohms only. The first point here is representation of resistance in time domain and frequency domain is same. There is no change. Sir, how about inductance and capacitance? We are going to see. So this is very simple. Understanding about resistance is very simple. It is not an energy storage element. Now, if you observe its Ohm's law, or it's a voltage current relationship. If you observe the voltage current relationship of resistance, does it is having any integrations? No. Does it is having any differentiations? No. Does it is an energy storage element? No. Now, come on here. Let's go for second element, that is inductor. Now this is very important. Okay, inductor. Yes, how to represent? Yeah, this is the symbolic representation in time domain. Yes, let me take the heading here in time domain. Come on, let me represent in time domain. Yes, this is L. What are the units of L, ma? In networks you might learn the units of inductance are henries. Now I am applying a voltage of VL of t across the inductor. Then what happens? Current of IL of t will flow. What is the relationship between voltage and current of an inductor? Come on here. VL of t is equal to L dIL of t by dt. So this is the relationship between voltage and current, or IL of t is equal to what, ma? 1 by L integral of VL of t dt. Here I have to stress on one thing, that is about initial condition. I explained clearly about initial condition. Initial condition is nothing but the initial energy that is present in the inductor. Inductor energy depends on what? Current. Therefore, what will be the initial condition of inductor current? Inductor initial current. If I am giving inductor initial current, then we have to take into consideration. If I did not give it, then it will be 0. So here, that's why I am not mentioning this integration limits. Actually, the integration limits must be minus infinity to t. Always we have to take minus infinity to 0 will mention initial value. Why? Because we are assuming that the operation is started at t is equal to 0. Always we assume, if the examiner did not given about the operation starting point, we always assume that the operation is going to start at t is equal to 0. The value that is existing from minus infinity to 0 is called as initial value or initial condition. Okay, yes, come on here. This is in time domain. Let's come into frequency domain. Yes, frequency domain representation. Come on here, ma. FD. This is frequency domain. Yeah, how to represent? First of all, take this equation, convert into S domain. Convert into S domain. How to convert into S domain? Laplace transform. Apply Laplace transform, brother. Yes, VL of t will become what, ma? VL of S is equal to, yes, L will be L. L will be L. You know, in Laplace and inverse Laplace, multiplication factor will remain same. Function is going to change. Function is going to change. Now, d by dt, I told you that instead of d by dt, what we are going to get, one s term. Suppose if it is d square by dt square, s square, we are going to get into s into I of t will be what? I of s. Yes, L into, please, L into s into I of s. Why I kept that bracket, you will be understanding now. If it is having any initial condition, s into f of s minus f of 0 minus, I told you, minus, what is f here? F, the function here is il, in fact, il of s, this is il of 0 minus. So this is how we have to write in what you call S domain. Assume that for time being, if il of 0 minus is equal to 0, if il of 0 minus is equal to 0, yeah, later we'll be considering that il of 0 minus also after completion of this one with initial conditions we'll take separately. Okay, formula is this one. You have to consider, suppose if it is 2 amperes, you have to put here 2 amperes. Okay, now what is VL of S? VL of S is equal to LS into IL of S. LS into IL of S. Observe here, I am going to put this one in a box. We have to understand few points about this relationship, that is VL of S is equal to LS into IL of S. Come on here. What are the units of this current? This IL of S units are what, ma? Amperes. What are the units of this VL of S? This is volts. Now come on, the relationship between amperes and volts. See, volts will be equal to what into amperes? Definitely ohms into amperes to satisfy units. Come on, brother, do not get confused. This is very simple. I think in your lower grade levels, in intermediate or in your diploma, you might study about units and dimensions. You know, voltage units is equal to, we have ampere here. What must be the multiplication factor? Ohms. Means LS is what? Having ohms as units. We will prove in another way also. See, this is indirect way. Volts is equal to amps into something, that something must be ohms. See, very simple, boss. To speak in a very simple language, 4 into x is equal to 2. How much must be that x value? 2, to satisfy that multiplication. Here we have volts, amps is there, into something is there, that something must be in ohms. Means a representation of inductance in S domain. Representation of inductance in S domain must be in terms of, yes, ohms. LS, this is in ohms. This is plus minus. This is VL of S. This is what, ma? IL of S. Now, inductor in S domain will be represented with LS, whose units are ohms. I told you that we will prove in another way also how LS units are ohms. Come on here. Very simply, I will be proving here LS units we want. What is S, ma? S is frequency. Which frequency? Complex frequency. We have to discuss about one more topic, that is introduction to complex frequency. We will be discussing after completion of this one. Okay, yeah. What are the units of S? Units of S are frequency. Frequency means what? 1 by seconds. Frequency means what? 1 by seconds. F is the frequency or S is the frequency. Its units are per second. In fact, frequency units are per second. Order maybe the frequency, its units are per second. Per second. Inductance units are what? Henries, you know, as far as you are concerned. its units are henries. But henries per second, maybe ohms are not. I'm in dilemma. Therefore, let me write henries in terms of other known. How to write? V is equal to L di by dt, right? V equal to L di by dt. Yes. Come on, boss. Very simple. So, interviewer may ask you, can you prove LS units as ohms? Yes. This question one time asked in IIS Bangalore interview. Yes. So, LS units, can you prove LS units as ohms? Yes, we can. Now, what is this units? Volts is equal to L units are henries, di amps by dt seconds. Come on, brother. I'm writing units here. Volts is equal to henries. Volts is equal to henries into amps per second. What I want? I want the units of henries. Now, what is this Henry? Henry is equal to volt second per amp. Henry is equal to what? Volt second per amp. Now, let me write here. Henry, substitute here. Volt second per amp into per second. Second gone. What you are left with? Volt by amperes. Volt by amperes means what? Ohms. LS units are ohms. This is the way how to prove this one. Okay. So please do understand this one. This is how we have to prove it. Now, one more important point I want to discuss here. See, V is equal to L di by dt is the relationship between voltage and current of an inductor in time domain. Yes, in time domain. Now, but whereas when it comes to frequency domain, what it became, VL of S is equal to LS into I of S. Differential equation became simple algebraic equation. Yes or not? And one more thing, can you apply Ohm's law in time domain for inductor? No. But here, simply it is converted to Ohm's law. The voltage current relationship of inductor became Ohm's law here. V is equal to amps into, why? Because no derivatives here, no integrations here. Therefore, this is also, this is amps, this must be ohms. Means I can apply Ohm's law directly for inductor in S domain. Can you write? See, can you write? I'll ask you one thing here. This is L, this is VL, this is IL. You can directly tell whether this is time domain or S domain. This is in time domain. Why? Because in time domain only, L will be represented as L. If it is in frequency domain, L will be represented with what, ma? LS. Come on, brother. Whose units are ohms? Now, come on. Can you write IL is equal to VL by L? Absolutely wrong. Bullshit. Why? Because units are not matching. And moreover, this is not the relationship between voltage and current of an inductor in time domain. But whereas, if you represent inductor in S domain, LS, this is VL of S, this is what? IL of S. Can I write IL of S is equal to VL of S by LS? Ohm's law directly? Yes. This is the first advantage of what we call S domain. I can apply directly Ohm's law to the energy storage elements. That is what are the two energy storage elements we have, inductor and capacitor, directly. Yes, this is the first advantage of S domain. Yes. Now here we did not yet discuss about initial conditions. We will be discussing later after completion of this one. Now, what is the next element we have? Capacitor. Next element what we have is a capacitor. Yes, here element. Come on, ma. Element. Here time domain. Yes, here frequency domain. Come on. What is the next element? Capacitor. Element is capacitor. Come on. How to represent? It's a pictorial representation is this one. So sometimes we saw this type of capacitor. What is the difference between representation of this capacitor and this capacitor? This is a polarized capacitor. This is non-polarized. Means you can connect the plus minus here, minus plus here. But here for this capacitor, you do not have that type of chances. Suppose if you purchase a capacitor, then here it is marked as plus. Here it is marked as minus. Definitely, always you have to connect here plus, here minus only. Suppose if you want to connect a DC voltage source, you have to connect it this way. Then only this capacitor will work. Otherwise, if you connect in a reverse way like this, the capacitor may damage. See, the representation of this one will represent a polarized capacitor. Means whose plate polarities are already fixed. In that way only we have to connect the source. We should not connect in another way. But here you can connect a plus minus or minus plus of a DC source. No issues. So that is the difference between polarized and normal capacitor. Come on here. Here This is C. What are the units of C? In farads. What is the voltage across capacitor? Vc of t. We applied some voltage across capacitor, that is called as Vc of t. Then what is the current that is flowing through the capacitor? Ic of t. Current that is flowing through the capacitor is what? Ic of t. What is the relationship between voltage and current of a capacitor? Yes, Ic of t is equal to, yes, C dVc of t by dt, or yes, come on, V equal to Vc of t equal to, come on, 1 by C integral Ic of t dt. This is the representation in time domain. If you look at it, we have some differentiations and integrations, but it is very difficult to handle differentiation and integrations. If you feel we will convert into S domain, in S domain those things will completely simply will become multiplications. Come on here, in time domain, in frequency domain, sorry, what is Vc of t? Vc of S. Vc of t is what? Vc of S. Now 1 by C is as usual 1 by C, but we have an integration here. What is the Laplace transform of integration? Yes, 1 by, yes, Laplace transform of integration is 1 by S. Laplace transform of differentiation is, yes, we already noted that one. Ic of t will become what? Ic of S. Ic of S. Now come on here, we have to do the previous analysis for what we did for inductor. The same we have to do here. What are the units of this one? Vc of S, volts. This one is what? Volts. What are the units of this one? Amps. This is units of this one are what, ma? Amps. Come on, ma. Units of this one are amps. Then what are the units of this one? Definitely it should be ohms. But yeah, volts is equal to amps into ohms. Now capacitor in S domain will be represented with what, ma? 1 by Cs. What are the units? Ohms. 1 by Cs, ohms. This is what? Vc of S. What is this? Ic of S is the current. I can apply Ohm's law directly, means I can write current is equal to voltage divided by impedance directly in S domain for capacitor also. Can you write here current is equal to voltage divided by what you call capacitance? Never current is equal to voltage divided by capacitance. Units will not match. Here capacitance is not capacitance here. Here capacitance is what? Impedance. Now one point I want to correct here. You can apply Ohm's law in time domain also for inductor and capacitor if the given sources are sinusoidal sources. If you are giving a sinusoidal source, capacitance is no more capacitance. In steady state, you have to represent capacitor with its reactance XC. You might learn these things in network analysis. And inductor will be represented with what? XL, where XL is equal to omega L, XC is equal to 1 by omega C. Okay, but come on here, Vc of S is equal to what? 1 by Cs into 1 by Cs into Ic of S. Ic of S units are what? Ohms. Now here if I convert this one, which is there in integration form, what is that? I say differentiation form, please, not integration form. Ic of S is equal to C into Vc of S. Yeah, Vc of S, S into why S we got, instead of differentiation we got one S term, minus, yes, Vc of 0 minus initial condition. You know it very well. Here we are not discussing about initial conditions. We will take initial conditions after completion of this discussion. Now representation of a capacitor in S domain is what, ma? 1 by Cs. 1 by Cs. Let us take one circuit in time domain, another circuit in S domain. Okay, then we are going to see what are the advantages of S domain one compared to time domain. Come on here. Come on here. Here this side I am taking it as time domain. This side I am taking it as a what? A frequency domain. Let me take the first circuit. Let me take the first circuit. Yes, in this I am taking. Come on. R. This is L. Yes, this is plus minus V of t. This is R in ohms. As it is in time domain, inductor should be represented as inductor. Yes, L in henries. What is this voltage source? V I of t. What is the current that is flowing in the circuit? I of t. Now let's write its equation. Let's write its equation. Now come on here. We are going to learn many beautiful things here, boss. Many beautiful things. Okay. Now for a mathematics student, only mathematics student, he knows differential equation as differential equation, but we are going to understand differential equation in a different way. Okay. Come on here. Let's write its KVL. KVL. All of you know how to write KVL. Minus V of t minus Vi of t, yes, plus R into I of t. resistance into I of t plus, come on dear, L di of t by dt. L di of t by dt is equal to 0. What is this equation? What is this equation? This equation is a differential equation. This is what ma? A differential equation. Means if I rearrange like this, di of t by dt, yes, plus r by L into I of t is equal to V I of t by L. Let us assume this one as equation 1. Equation 1 is a differential equation. If you want the value of current in the circuit, what to do? Solve this differential equation. Every differential equation is going to have two solutions. One is complementary function, another one is particular integral. So you have to solve for complementary function and particular integral to get this I of t. Yeah, before we go for that, let us understand what is the differential equation. Differential equation is the one which gives the relationship between variables and parameters and the input of the particular circuit in terms of differentiations. Yes, means this is the governing equation of this system. Means if this system is given or this equation is given, we can say see this equation is given to us. I can say this equation belongs to a series RL network just by looking at this equation. Means this is the governing equation of this system. Means if you solve this, you can get any variable of your requirement of this system. Means this equation governs this system. We got this equation from this system. Why we got differentiation? Why? Because I have an inductor here. Imagine if there is a resistor here, what you are going to get? What you are going to get? No differentiation. Minus V of t plus R1 into I of t plus R2 into I of t. Does that is a differential equation or it is an algebraic equation? That is going to be an algebraic equation. First point what we have to understand here is we will get integral or differential equations or simply integro differential equations if and only if the system is going to contain what? Energy storage elements. If there are no energy storage elements, we are not going to get integral or differential or integro differential equations. Means simply differential equation is the governing equation of a dynamic system. I introduced a new what you call word here, dynamic. Dynamic means having energy storage or memory. Yes, inductor is having some memory. Memory means it is going to store. See, please do not compare human memory with element memory. Okay, see that is also memory, this is also memory, but here memory means storage. Here memory means what? Storage. Now this is the new way of understanding differential equation. Differential equation is the equation which is going to govern a dynamic system, and that equation will give the relationship between parameters and variables of that system. Yes, this is giving how the current and RL and input voltage are related in this system. Okay, we get differential equations only for energy storage elements or dynamic systems. For the systems which are containing energy storage elements, please write down these points on your own. I am not writing on board. Now this yeah, I am writing here to solve. We will take a frequency domain in another page, not a matter. First let's complete this one. Yeah, if we want to get, if to find I of t, I am writing here to find I of t from equation 1. Yes, we have to solve what we have to solve equation 1. We have to solve, yes, equation 1. See, I of t is going to have two solutions. One is particular integral, another one is a complementary function. Particular integral and complementary function. This complementary function is also called as natural response. Sir, why it is called as natural response? In third chapter, when I am discussing about time response, we will be giving good clarity there. Okay, this is also called as what? Natural response. Natural response. Yeah, C dot of means complementary function. You know from mathematics, that's why I am writing in a short way. This natural response is a new term, or it is also called as source free. What is that? Source free response. Source free response, or it is also called as force free response. Force free response, or it is also called as autonomous autonomous response. It is also called as what ma? Autonomous response. Many names it is having. Please do remember all the names. The justification of that name for this complementary function I will be giving you either in third chapter or in fourth chapter stability. Most probably we will be discussing in third chapter itself. Okay. This particular integral is also called as forced response. Forced response. That is called as natural response. This is called as forced response, or it is called as output due to input. Output due to input. Yeah, it is called as output due to system poles. Due to system poles. Please note down what does it mean by pole. We will be discussing later why all these names. Definitely I'll give clarity for everything. I will give you clarity. Okay, so solving a differential equation is very easy or difficult? It is difficult for us. Yes, it will be time taking process even. Yes, solving differential equation is a time taking process. Now one note point I want to write here, what we learned already. Yes, the KVL and KCL equations of, come on, the KVL comma KCL are the governing equations of equations of dynamic systems. Yes, dynamic systems. Underline this dynamic. What does it mean by dynamic ma? Containing energy storage elements. Dynamic systems are integro differential equations. Yes, we proved it. We got a differential equation. If we take an RL network and we wrote it's a KVL, we got differential equation. Yes. If I take a static system, for example, example of static system. Yes, simple example. This is R1 and R2. Let's close this one with VA of t. In time domain only. We are in time domain. VA of t, R1 and R2. This current is I of t. Write its KVL. If I write its KVL, yes, minus VA of t. Come on, ma. Plus R1 into I of t plus R2 into I of t equal to 0. This is equation 2. Equation 2 is an integral differential equation or algebraic equation. Equation 2 is yes ma, algebraic equation. Means I can simply say the governing equations of completely static systems are algebraic equations, which are easy to solve. Algebraic equations or differential equations are algebraic equations. That's why purely resistive networks are very easy. DC analysis is easy when compared to AC analysis and transient analysis in your networks. Now in time domain, I got differential equation. Let us convert the same circuit into frequency domain. Yes, I'm taking here frequency domain. The same circuit I'm taking here. What is that? So this is resistance. This is inductance. Yes. This is plus minus. Yes, this is current. Come on here. VI of t. Yeah, go back there. The same system we are comparing between time domain and frequency domain, please. Therefore, say the same system I have to take. VI of t will become there. VA of S. R only. L will be LS. What are the units? Ohms. I of t will be I of S. Come on here. I'm writing VI of S. R is in ohms. R is in ohms. LS is in ohms. I of S will be I of S. I of t will be I of S. Let's write its KVL. Minus VI of S plus R into I of S plus LS into I of S is equal to 0. This is equation 3 I call. Yes. The KVL equation of a dynamic system in S domain is an algebraic equation, whereas the same system equation in time domain is what? Algebraic equation. First advantage of this S domain is integral differential equations in time domain will become algebraic equations in S domain. How to get I of S? I of S is equal to, very simple, VA of S by R plus LS, simply Ohm's law, or you can solve this KVL. See, take I of S common and you segregate it, you are going to get I of S is equal to VA of S by R plus LS, or write Ohm's law, because these units are ohms, these units are also ohms, therefore we can write Ohm's law directly. I of S is equal to what? VA of S by R plus LS. Done. Now, which one is easy? This one is easy. There I have to find complementary function, particular integral. But here, just simply an algebraic equation and solve it. If you want I of t, what to do? If you want I of t, what to do? L inverse of I of S will give I of t. This is why we learned Laplace and inverse Laplace transforms. Simply, I'm going to write a note point. Yes. Integral differential equations in time domain. Integral differential equations in time domain will become, yes, algebraic equations will become algebraic equations in S domain. Yes, this is the first great advantage of what you call S domain. As I have units as ohms and ohms, I can apply Ohm's law directly. There also I can apply Ohm's law, but if only for sinusoidal inputs. If the input is sinusoidal, then there also L will be represented with omega L, C will be represented with 1 by omega C, more or less equal to the same. This frequency domain analysis only. Okay. AC analysis is equal to frequency domain analysis. Why? Because the input what we are giving in AC analysis is a frequency input, that is sin omega t. Okay, come on here. This is the advantage of S domain. This is the first one, and we can apply directly Ohm's law. Whatever may be the input may be impulse or step or ramp or parabolic or like exponential or whatever it is, we can apply directly Ohm's law. So these are the advantages of S domain. One more very big advantage of S domain we are going to see. For that one, we have to understand one concept of signals and system, that is convolution. Yeah, brother, remember one point here. I'm not going to explain what is the physical significance of convolution here, because it takes a lot of time for us. In signals and systems, you will be learning what is convolution, what is its significance, and all those. Here, if you want, please message me or call me or mail me. Definitely, I will be explaining you about the convolution physical significance. See, just like that, it can't be explained. It will take a lot of time. It is not our cup of tea to learn convolution here. Just what is the application of convolution in time domain and frequency domain? How to convert from time domain to frequency domain and frequency domain to time domain? Those statements only we are going to understand. Yeah, our heading is convolution. Next property is what? Convolution. Property is what? Convolution. First, let's discuss in time domain. And after that, we'll discuss in frequency domain. Come on, here. Observe all of you here. I have a system whose response is h of t. You might got a doubt. Sir, what is system? What is that system response? System response is also called as impulse response. We will be understanding in the upcoming chapters, in the upcoming sessions, not chapters, please. H of t is called as system response, which is also called as impulse response. Okay, we will see. For time being, we have taken a system. In fact, that is an LTI system. We have taken LTI system whose impulse response is h of t. I am exciting this system with input r of t. See, input is also called as excitation or stimulus or desired output. Why these many names? What are the meaning of those names? Also, we are going to see in the upcoming sessions. Yes. Then what we are going to get? We are going to get the output C of t. If I ask you what is C of t, many students will give the wrong answer. That is, they'll say that C of t is equal to. They will say that C of t is equal to R of t into H of t. They will say R of t into H of t. They will say absolutely wrong, brother. R of t into H of t. They will say absolutely wrong. Yes, it is not R of t into H of t. this is r of t in convolution with yes in convolution with, this is the convolution symbol ma, that is convolution symbol. Yes, what is this means input given to a system, then the output is input response in convolution with system response or impulse response of that system. Why it is you will be learning in signals and system, you will be learning in signals and systems. But what is this? This is a symbol of convolution. This is a symbol of convolution. Expand it means what does it mean? How to calculate it? How to calculate it? Let's see. How to calculate it? Let's see. C of t is equal to, important to remember. Anyhow, you will be learning this one in signals and systems. Yes, r of t. See, integral of 0 to t. Integral of 0 to t. R of tau. R of tau. I will be explaining this process. R of tau into h of t minus tau d tau. H of t minus tau d tau. Yeah. What is the first thing we have to do? We have two signals here. One is r of t and h of t. Replace that t with a new variable called tau. First, take r of t. Then replace with a new variable tau. Take h of t. Yes. Replace with a new variable tau. H of tau. H of tau. H of tau. Then after replacing with new variable, what I want h of minus tau. I want what? H of minus tau. Then what to do? Time reversal it. H of minus tau. What is the next step? Time reversal it. After that you shift by what? T. Shift by a value of t. Then what I'm going to get? H of t minus tau. Yes, we got this one. We got this one. Now come on here. What we got? We got this one and this one. Both what I have to do? Multiply. After multiplying those two, what we have to do? Integrate from 0 to t. This is the procedure how we will get convolution. Or see, or we have one more way also. We have one more way also for the same convolution. I think all of you understood this procedure. First, take both the functions, replace with a new variable. That h of t, whatever it is there, replace with a new variable, time reverse it, shift it. Then you multiply both the functions, then you integrate from 0 to t. Or another way is also there. Another way is also there. Let's see. Or come on, that is c of t is equal to yes. Instead of h of t, we'll do r of t now. C of t is equal to integral of 0 to t r of t minus tau. R of t minus tau. Yes, r of t minus tau into h of tau d tau. Means previously we did for h of tau that time reversal, shifting, multiplication and integration. Now here what you do for r of t. What to do? R of t, you just you make it as r of tau. Change the variable from t to tau. Time reverse rate r of minus tau. Shift it t minus tau. Then you multiply with the h of tau. Then you integrate it. Look at this. Does this process looks easy or difficult? Difficult because too many steps are involved. But do not take it granted it is difficult for all problems. There are some problems which can be solved by this integration within one step or no steps. That depends on the question. But most of the questions, for most of the problems, practical problems, going in this way to find the output C of t is going to be difficult. There are some exceptions where this process is easy. Okay, that's why I am not generalizing it. Mostly this is going to be difficult for us, but there are some problems or some places where this process is going to be easy. We will see those problems also. Okay, so this process is easy or difficult because one of the important and difficult procedure is integration. Suppose if we got two functions which are both derivatives are keep on existing, then it is going to be very, very difficult for us. Okay, then what is the procedure in S domain? This is in time domain. The same procedure in S domain, frequency domain. I'm writing here frequency domain. Yes, take the same system. Take the same system here. Yes, take the same system. Now h of t will become what ma? H of s. H of t will become what? H of s. The same convolution in frequency domain I am discussing. H of t will become h of s. R of t will become what ma? R of s. C of t will become C of s. Yes. When you apply Laplace transform, R of t, R of s, H of t, H of s, C of t, C of s. Then what is C of s? C of s is equal to R of s into H of s. Yes, this is the greatest advantage of S domain. Simply, I am going to give you a note point. difficult convolution in time domain will become simple multiplication in S domain. It's very, very, very important note mind. You might got a doubt, sir, what is a proof for that? I told you that you will be learning along with proof in signals and systems. Okay, note point, please. All of you must remember this note point. That is convolution test. Convolution in time domain. Time domain will be converted to yes, converted to what ma? Multiplication what ma? In S domain. Now you tell me which is easy, convolution or multiplication. In convolution we have to time reverse it, shift it, multiply it, integrate it, lots of process. Here just you multiply R of S and H of S. But what is the only one extra step? Sir, I want C of T only. But we are getting C of S here. Then C of T is equal to how to find L inverse of C of S. This is the reason why we mastered all inverse Laplace transforms and Laplace transforms. Okay, sir, I want ultimately answer in time domain, but if you convert into S domain, you are getting C of S, but I want C of T. What to do? Apply inverse Laplace transform, and vice versa, please, and vice versa, and vice versa. What is vice versa? Suppose if you have convolution in S domain, that will become multiplication in time domain. Okay, if you have convolution in S domain, means I want to convolve two signals which are in S domain. That is my requirement. Therefore, convolution will be convolution, means integral of 0 to, instead of t, we are going to take for s, and h of s, r of s minus some x, we are going to do it. In convolution in S domain will become multiplication in time domain. See, one domain convolution, another domain multiplication. One domain multiplication, another domain convolution, vice versa. But here in time domain convolution is becoming multiplication in S domain. This is the third greatest advantage in S domain. First advantage is the integral differential equations will become simple algebraic equations in S domain. Second one is directly I can apply Ohm's law, whatever, irrespective of the input that is given to the circuit, without knowing what you call the knowledge of input and all these things, I can apply directly Ohm's law. Okay, and third advantage is this one, convolution will become simple multiplication. So these are the reasons why we entered into S domain. There are a lot of advantages. When time comes, at the time we'll discuss. So with this, we are done with a representation of RLC, and without initial conditions. With initial conditions, we have to see. Let us see with initial conditions. There are some problems where some of the times with initial conditions will be given. In transient analysis, mostly a given transient question, if it is looking very difficult in time domain or in time response analysis or in time domain approach, means you are writing I of t is equal to some equation in terms of t. If you are writing, that may become difficult. At that point of time, this one S domain analysis is going to give the answer to you very easily. But you have to choose the procedure. Means you must be in that level that by looking at the problem, which method, either time domain approach or frequency domain approach, is going to give simple and short answer to you. Okay, so that you will get by practice. Always you practice, then definitely you will get that mastering in the subject. Now come on here, with initial conditions, representation of inductance and capacitance, we are going to see here. With initial conditions, first let's take inductor. Yes, first one is inductor. Capacitor is not going to have any initial condition. Inductor, so its initial IL of 0 minus is equal to I naught. I'm giving IL of 0 minus is equal to I naught. I'm giving, means I have an inductor. Yes, this is L in henries, and this is having initial current of I naught. But to this one, I am giving a voltage of VL of t at t is equal to 0. Before t is equal to 0, this VL of t is not there, but there is some current I naught here. You have to understand very carefully. See, this is the input that we are giving at t is equal to 0. Yes, let me represent here. This is VL of t. We are connecting this input to this inductance at t is equal to 0. Before t is equal to 0, there is some current. Yes, I'll mention here IL of 0 minus is equal to I naught. IL of 0 minus is equal to I naught. This is L in Henry. Now, first of all, let's understand the representation in time domain itself. Understand the representation in time domain itself. Now, this inductor is going to have two currents. One is the previous current. Second one is the present current. Yes, one is the previous current. Another one is the present current. Now, IL of t is equal to I'll write integral of 1 I is equal to 1 by L integral v dt. See, v is equal to L di by dt. I is equal to 1 by L integral v dt. Now, I'll write in this way. 1 by L integral minus infinity to t VL of t dt. VL of t dt. If you observe, this VL of t is present from 0 onwards, not from minus infinity onwards. Then I am splitting this integration like this. 1 by L integration from minus infinity to, or do not write any bracket, not required. Yes, 1 by L integral minus infinity to 0 VL of t dt plus 1 by L integral 0 to infinity VL of t dt. Yes, this is the splitting of this integration. Now, if you observe, most of the students will give the wrong answer like this. Sir, VL of t is not there before t is equal to 0. Therefore, I substitute t is equal to 0. I am going to get 0 here. Yes, you can substitute if this initial current is not there. This VL of t may be the voltage previously which is appearing across this switch. This VL of t, both are not same place. This VL of initial before t is equal to 0, this voltage what? See, the voltage that is present across inductor is called as voltage across inductor. So this is the voltage across inductor before closing the switch. There may be some voltage. But this total is nothing but initial current IL of 0 minus. So I will be writing like this. Come on here. IL of t is equal to, means current through inductor at any point of time after closing switch is equal to previous current plus present current. What is present current? 1 by L integral 0 to t yes VL of t dt. Means we connected a source now at t is equal to 0. That will give this much of amount of current. Already is having some previous current. Simply here you have a bucket. In that 2 liters of water is present. Now we have a bucket. In this already 2 liters of water present. 2 liters. Okay. Now at t is equal to 0, we are keeping this bucket under a tap, which is giving, this tap is giving 2 liters for 1 hour. Okay. If I ask you what is the total water content in this bucket after 2 hours, means initial water is 2 liters. When I am asking after 2 hours of closing the switch or opening this tap, for 1 hour how much is the water it is going to give? 2 liters. After 2 hours how much it is? 4 liters. Total is how much? 6 liters. The total water in this bucket is 6 liters. In this way, previously we have some current in this inductor, that is the initial current. Now present given source is giving some current, that is this current. Means the inductor is having two currents in addition. Means it may be in reverse way. See, the IL of 0 minus may be plus amperes or minus amperes, we don't know. If this may be plus, this may be minus, this may be minus, this may be plus. Both are plus or both are minus. We are least bothered about their values. That value depends on the particular problem that what you taken. Okay, do not generalize here. Two currents are in addition. Do not understand getting aided. Maybe aided or subtracted, but we will take plus symbol. That current direction will take care of that. Okay, so I have to represent like this. Two currents will add in parallel or in series. In parallel only currents will be added. Therefore, what I will do is, now I will represent inductor. L in Henry, and this is IL of t. I call from 0 to infinity, from 0 to t, not infinity please, from 0 to t. Yes, in parallel with we have another current. What is that? We have what? I naught. Yes. So this is the total inductor current. Let me erase this one and we will write again. Yes, sir. Now come on here. Come on, all of you. Here, this is IL of t. IL of t is I naught. This plus this current. What is this current? This current is 1 by L integral 0 to t. This current is. This is simply I call that one as I1. just for our representation purpose only, please. Representation purpose only. You should not misunderstand. Okay, that is I or I1 I call I1. So the total current IL of t is equal to I1 plus I0. This is how we have to represent the inductor with initial conditions. This is VL of t. This is what, ma? VL of t. VL of t. Yes or not? Total current is what? This plus this. Now convert into S domain. Convert into S domain. Now this is important for us with respect to control systems or network analysis transitions. Converting into S domain. Understand this one, why I kept, some people will misunderstand, sir, why we connected a current source here. I did not connect any current source. I want to represent what is the current that is present in the inductor previously. I am splitting this into total two currents. One is previous current and one is present current. This inductor will represent present current. This current source will represent the previous current. This total is the inductor current. Sir, why you take an arrow down? Because current I have to add. This is down, this is also down, both will be added. Okay, now in S domain, in frequency domain, yes, now come on here, the same I'm representing like this. This will be Ls in ohms, Ls in ohms. This current to the down, I0 will be written as, come on ma, I0 by S, I0 by S, yes or not, I0 by S. This is what VL of S. VL of S. LS. Why? Because we know very well inductance in frequency domain will be represented with LS and its units are ohms. This is a constant. Yeah, this is a constant. Then what is the Laplace transform of unilateral Laplace transform of 1 by S? Therefore, that is what I0 by S. I0 by S. Now, this is in ohms. This is in amperes. If current source is in parallel with impedance, yes, something you have to get in your mind. What is that? What is that something you have to get in your mind? That is a source transformation theorem from network analysis. Voltage source in series with impedance or current source in parallel with impedance will be converted to voltage source in series with impedance. Now I'll redraw and we'll see. I'll redraw and we'll see. Come on. This is what we have. This is what we have. This is I0 by S to the down. This is Ls in ohms. Yes. This is, come on ma, this is plus minus VL of S, plus minus VL of S. This is the total current I of S. Let us convert this into volt. See, let us transform this, not convert, transform. What we are doing? Source transformation theorem we learn. Current source in parallel with its impedance will be converted to voltage source in series with its impedance. Yes. Now if I do that, by using source transformation, this is equivalent, please. Yes. Now this is plus minus VL of S. Yes. Now we are going to get some impedance Ls in ohms. Now we are going to get voltage source here. What is the value of voltage source? This into this. I0 by S into Ls. S has gone. How much we have? I0 L. Now the question here, sir, whether it is plus minus or minus plus, that is very important. Sir, whether it is plus minus or minus plus, it should be minus plus. So why not minus plus? Why? Because current is flowing in the downward direction. This I0 is in the downward direction. A voltage source will give current from positive terminal. Therefore, I need to take minus and a plus. Now tell me, what is VL of S? VL of S is equal to, what is this? This one is I of S more. Ls into I of S minus I0 into L. If you remember, we wrote this one previously. Come on. Or why to go there? Just here itself we can write what we got. V is equal to L di by dt we have. Now if I apply Laplace, V of S is equal to L into S into I of S minus initial current I of 0 minus, that we are writing it as I0. That we are writing it as what? I0. Yes. That L will go inside. Come on, this is very simple. V is equal to L di by dt. The VL, in fact, VL of t, this is in time domain. Okay, VL of S. Yes. Ls into IL of S minus I0. If you throw this L inside, these both are exactly matching. Okay. So this is how we represent inductor with initial conditions in S domain, either this way or this way. Now in the same way, let's understand a capacitor with initial condition. What is the initial condition of a capacitor? Voltage across a capacitor is the initial condition of a capacitor. Come on here, let's discuss capacitor. Yes, capacitor with initial conditions. Now let me draw. Observe here. This is capacitor. Yes, C in farads. Plus minus V0 is the initial voltage. Now the present voltage that is applied across capacitor is Vc of t. Present voltage that is applied across capacitor is Vc of t. Now right here, Vc of t is equal to voltage across capacitor at any point of time after t greater than 0. Here we are connecting this one at t is equal to 0. This one we are connecting at t is equal to 0. We are closing the switch, please. We are closing the switch. Switch close means this direction at t is equal to 0. We are closing the switch at t is equal to 0. Or let us redraw this one, man. Let us redraw. Yes, I have a capacitor. It is containing an initial voltage of V0, and we are applying a voltage source of Vi of t, and we are closing the switch at t is equal to 0. We are closing the switch at t is equal to 0. This is capacitor whose value is in farads. Now let's write very simply from statements what we understood. Present voltage is equal to previous voltage, and the obtained voltage due to new source means simply Vc of t is equal to 1 by c integral minus infinity to t Ic of t dt, I of t dt. V equal to 1 by c integral I dt. If I split it, 1 by c integral minus infinity to 0 Ic of t dt plus 1 by c integral 0 to t, yes, Ic of t dt. Yes, now this is nothing but initial voltage V0 plus 1 by c integral 0 to t, yes, Ic of t dt. Yes, this is the value that we have. See, this side voltage across capacitor, then definitely this is also voltage across capacitor. This is also voltage across capacitor, but we are taking integration from minus infinity to 0 means that is the previous value. But because we are closing the switch itself at t is equal to 0, the one that is present from minus infinity to 0 will be initial value. How much is that initial value we taken? V0. Sir, if it is 0, if the examiner mentioned the system is initially relaxed or initially at rest or its initial conditions are 0, therefore this is going to be 0. This is the present value. Let's represent in S domain. So capacitor, this is 1 by Cs, or first let's represent in time domain itself. In time domain itself, I can represent like this. Yes, plus minus, this is V0, this is plus minus Vc1 I call, yes. Now this is plus minus Vc of t I call. Let me put a switch here. Yes, we are going to keep a switch, and that switch is closed at t is equal to 0. Now let me write Vc of t is equal to Vc1 plus V0. What is Vc1? Vc1 is the voltage that is developed across capacitor when the switch is closed at t is equal to 0. Then plus V0, previous voltage. Okay, previous voltage. What is Vc1? 1 by c integral 0 to t Ic of t dt plus V0. Why we kept both in series? Why? Because previously for inductor, currents are getting added, means currents are in adding position. Why? Present current plus previous current is equal to total current. Here voltages have to be added. In which circuit connection voltages will add? See, number of times in interview these questions are asked. The interviewer will ask you like this: represent a capacitor with its initial voltage. Then you will draw this diagram. Immediately the examiner will ask you, or the interviewer will ask you, why you are connecting both in series? What is this one? This is the voltage source you are connecting? No, this represents the initial voltage that is present in the capacitor. Why we kept in series? Why? Because both are in adding position. Means total voltage at this point of time is equal to initial voltage plus the voltage that is developed from 0 to present time. That's why we connected in series. Now let's convert into S domain. FD, please, frequency domain. Yes, what we are going to get? this is plus minus, come on ma, Vc of s. So this is the switch that is closed at t is equal to 0. Yes. Now this will be what ma, 1 by Cs. Units are ohms. What is this? What is this? V naught by S. V naught by S. Both are in addition form. Plus minus will get add. S V naught by S. Now observe here. This is the representation in S domain. Now if you observe, we have some ohms in series with voltage source. I can apply source transformation theorem here. Previously, current in parallel with impedance is converted to voltage in series with impedance. Here I have voltage in series with impedance. If I want, I can convert this one. Yes, if I want, I can convert this one into current in parallel with impedance. You can convert and check. You are going to get a current source. What is the value of current source? This by this, please. V naught of S by, see, what is I of S? If you want to represent in terms of I of S, what is that? V naught of S by 1 by Cs. So this gone. That is V naught C is the value of current. The direction of current should be to the down or up? To the up, please. To the up. Let me represent here. That is current source. What is that? V naught into C in parallel with what ma? 1 by Cs. 1 by Cs. Units are what? Ohms. This is plus minus Vc of S. Plus minus Vc of S. So this is how we represent a capacitor in S domain with initial conditions. Now we are done with inductor and capacitor, resistance in time domain and frequency domain, convolution, all these things. 99% of Laplace domain or S domain is done with us. We solve some problems also. We will be solving few more problems, and few more problems are given as CRQs. What does it mean by CRQ? Concept revision questions. What are all the concepts we learned here to check your concepts, whether you learn in a correct way or not. Some questions will be given. So for every class we will be providing some 10 questions as CRQs. Please solve those questions. Along the questions, key also will be given to you. Check your key with the faculty key. If not matching, you can get back to the faculty. Now, one more simple concept, that is introduction to complex frequency. See, this is not important with respect to examination. This is very important with respect to concept and interview. I will tell you where to replace S is equal to 0. I told already this one. S is equal to sigma, S is equal to sigma plus j omega. Where we have to substitute all those things, let us see. So my heading is introduction to complex frequency. Very important concept with respect to interview, or if you want to have good clarity on what you are doing, then definitely this topic is required. Introduction to complex frequency. Yes, introduction to complex frequency. I will be discussing only few basics. I'm not going to draw all the graphs and all those things. Yeah. See, a generalized signal I'm going to give. A generalized signal. Suppose a signal means either it may be voltage or current. Let me take it as voltage. We'll take it as voltage. We'll speak in terms of voltages. Or you can take it as x of t or y of t. That is your response. But being electrical and electronic engineers, we know signals means voltage or currents or power and all these things. Come on here. So some v of t, for example, I'm taking voltage. Some k, or let's not take any k. K may be any value, or it may be a constant, whatever it is. E power, or let's take k, no issues. Some k into e power sigma t into sine of omega t plus phi. Sine of omega t plus phi. This is the signal what we have. This is called as a general signal. Sir, why it is called as general signal? General natural signal. Why it is called as general signal? From this one, I can get any signal that I require. I can get DC, I can get exponential, I can get sinusoidal. Yes, these three basic signals I am able to get from this one. If you get DC, if you integrate it, you are going to get ramp. If you differentiate it, you are going to get impulse. If you are double integrated, you are going to get parabola. Yes or not? Yes. So how to get what you call DC from this one? How to get DC from this one? Yes, this is the general signal. Yes, general signal. What is this omega? Omega is the angular frequency. You know it very well. Sine 2t, sine 3t, sine 4t. Phi is some phase shift that may be 0 or positive or negative. What is this sigma t? Sigma may be any value. Sigma may be any value. Suppose if this is e power minus 2t, what is sigma? Minus 2. Suppose if this is 1, What will be sigma? Sigma equal to 0. Sigma equal to 0. Now come on here. I want to get, yeah, I told you one point that any signal of your requirement, either DC or exponential or sinusoidal or exponentially decaying sinusoidal waveform, you can get from this one I told you. Now the first question raised by a student is, sir, how to get DC signal? How to get DC signal? Yes, first question is obtain DC voltage, yes, from P of t. From V of t, yes, he's asking to get DC. Now, how to get DC? DC means a constant value which is not changing with respect to time, neither decrement or increment. It should be constant. Now, V of t is equal to DC if sigma equal to 0, comma omega equal to 0. Sigma equal to 0 and omega equal to 0. Yes, check it. Check it. If sigma is equal to 0, what is V of t? V of t is equal to k into e power 0 into t. Yes, into sine of omega into 0 plus phi. What is this ma? K into sine phi. Phi is a value. So it may be 30 degrees or 60 degrees or 120 or 180, whatever it is. K into sine phi. This is what? Constant. This is what? Constant. We obtained DC signal if we substitute sigma is equal to 0 and omega equal to 0 in this general signal. What is vice versa? If you want DC, substitute S is equal to 0. Substitute what? S is equal to 0, where S is equal to sigma plus j omega. Means I am writing over here. Yes, S is equal to sigma plus j omega. Why we got S is equal to sigma plus j omega also we are going to see in very short time. S is equal to 0, that is sigma is equal to 0, comma omega equal to 0 for DC analysis. Means our applied input is DC to a given system or circuit, then we have to substitute S is equal to 0. S means what? Sigma and j omega. Sigma also 0, sigma 0, omega also should be 0. So this is about DC analysis. Sir, I want steady state sinusoidal AC analysis. See, we have to understand this point. Steady state sinusoidal AC analysis means sigma should be 0, omega should be present. Means, come on here, come on. I will draw. If sigma equal to 0, comma omega equal to 0, I am drawing this V of t waveform. Come on, this V of t waveform. Here I will be taking V of t. Yes, this is V of t. This is 0. Yes, this is the signal. What is the magnitude we got? K sine phi. By assuming that K and sine phi both are positive. If negative, if any one of those two is negative, it will be downside. If both are negative, it will be upside. And one more thing, here x, this point I am representing as 0 and I am not representing this one as a 0 value. Okay, it may be either up or down. But one point you have to understand here is this is a DC signal, pure DC. Now, come on here, sir. I want pure AC. What does it mean by pure AC? See, AC means alternating current, but I want the magnitude to remain same. Means positive peak and negative peak should be constant. Yeah, it is varying with respect to time, but positive peak and negative peak should be consistent with respect to time. I want that. What to do? V of t is equal to what we take in k into e power sigma t into sine of omega t plus phi. If sigma equal to 0, what we have? V of t is equal to k sine omega t plus phi. K sine omega t phi is nothing but pure AC. Come on, let me draw here. This is omega t. If you take, this is V of t. Let me draw the figure, please, with some phase shape, yes, in this way. Yes, this is what we got. This is k sine phi. What is the maximum possible value of this one? For omega t equal to 90. For omega t equal to 90. See, what is the maximum value of this one? K. Minimum possible value minus k. Minimum possible value is minus k. So that is plus k. This is minus k. Yes or not? Yes. So we got pure AC. Means if we want a pure AC analysis or an AC analysis. See, this is our note point. For AC analysis. Second note point, please. For AC analysis. Put sigma is equal to 0. That implies what? S is equal to j omega. Very, very, very important with respect to our application. See, if you see, many faculties or many students know just to substitute S is equal to 0 for DC. They don't know why we have to substitute S is equal to 0. They don't know why sigma should be 0 for AC analysis. For AC analysis, S is equal to j omega. sigma should be 0. Sigma should be 0. Sir, I want an exponential signal. I want exponential signal. Yes, sir. Next one is for exponential. If for v of t to be exponential, for v of t to be exponentially, let's take exponentially decaying. Exponentially increasing signal is an unbounded signal. Let's take exponentially decreasing. Exponentially decreasing signal. Then come on, what is the v of t we have? K into e power sigma t into sine of omega t plus phi. Substitute omega equal to 0. Substitute omega equal to 0 and sigma some negative value. Sigma some negative value means for exponential analysis you have to substitute omega equal to 0. Then what v of t you got? V of t is equal to k into e power sigma t into sine phi. That k is constant, sine phi is also constant. I'll write that one as k1 into e power sigma t. I'm writing if sigma equal to minus 2, suppose say if sigma equal to minus 2, what we have? V of t is equal to k1 into e power minus 2t. Exponentially decreasing signal. Come on, you see, we got exponential, sinusoidal, and what you call DC. Sir, I want exponentially decaying sinusoidal waveform. What does it mean by exponentially decaying sinusoidal waveform? I'll show you that one. This is t. This is v of t. How the waveform looks? Exponential decaying sinusoidal waveform. This is the exponential decay. This is the exponential decay. Yes, in this envelope. Yeah, this is called an envelope. In this envelope, if sinusoidal waveform is there, yes, this is called an exponential decreasing sinusoidal waveform. If you understood your mathematics, so suppose if I take this one as v of t, yes, we are taking this one as v of t. V of t will be some exponentially decreasing into sine of omega t plus phi. It may be some, why I taken minus 2? Minus 2 is not standard this. To represent that negative value I taken. Exponentially increasing means some k. In this one, s is equal to sigma plus j omega. Both must present. S and in s, sigma and j omega both must present. Otherwise, you won't get this exponentially decaying or increasing. How exponentially increasing will exist? Suppose if you are taking, we'll take the function also. V of t is equal to some k into e power 2t into sine of 2t plus phi you taken. E power 2t is increasing. How it is increasing? Exponentially. It is increasing exponentially. Let's draw its envelope. Exponential increment will be like this. Yes, exponential increment will be like this. And a sinusoidal. Yes, sir. It has to increase exponentially, but the waveform is what? Sinusoidal waveform. Now let us draw that waveform, please. Yes. In this way, observe, waveform is increasing exponentially but making sinusoidal oscillations. These are called as undamped, or what you call uncontrolled oscillations. Whose value is tending towards infinity finally. Yes, these are called as damped oscillations. A damping means a killing or reducing, suppressing or reducing. In fact, the better word to understand is reducing oscillations. Magnitude is reducing. These are unbounded oscillations, though there are no bounds. Keep on increasing. Means with this we got with the generalized expression we got AC, DC, exponential and exponentially decreasing and increasing waveforms. That's why it is called as a general expression. Now let us take this one. V of t is equal to what? Some k into e power sigma t into sine of omega t. Yes, our general expression. I am taking phi is equal to 0 for my simplicity. For the simplicity purpose, I am taking phi is equal to 0. Apply Laplace. What we are going to get? A capital V of s, please. Laplace is always capital. V of s is equal to some k into. Yes, apply Laplace. Very simple, boss. Very simple. What is the Laplace of this omega sine omega t? Omega by, yes, come on, s square plus omega square. But as I have one exponential in time domain, if we have exponential in time domain, in frequency domain, we are going to get what? In frequency domain, we are going to get type shifting. In frequency domain, we are going to get what? Shifting. There it is plus here. What it is here? Minus. Then now, what are its roots? We found its what? S domain formula, or We convert from time domain to frequency domain. What are its roots? Denominator roots I want to find. Denominator equation of a transfer function is called as characteristic equation. Or let's not bother about transfer function and characteristic equations. Later we are going to see what are the denominator roots. The equation of the denominator is this one: s minus sigma whole square plus omega square is equal to 0. If you simplify this one, you are going to get s is equal to sigma plus or minus j omega. This is the reason why you have to substitute s is equal to sigma plus or minus j omega. S is equal to sigma plus or minus j omega. Let me list out all the points, please. I think all of you understood why we have to substitute s is equal to sigma plus j omega. Why? Because our generalized function roots are sigma and j omega. S is called as complex frequency. Yes, omega is frequency, then this sigma also must be a frequency. Therefore, S is called as complex frequency. Complex frequency means it is going to have some real part and imaginary part. Here, two interesting points I want to tell you. If you observe, S is equal to sigma plus j omega. Yeah, I have real part and imaginary part. Let's understand the difference between mathematics and engineering. Omega is imaginary part of complex frequency. Let me write here. Omega is, interview question, brother. Omega is imaginary part of complex frequency or S. Complex frequency. Yes, omega is imaginary part of complex frequency. People will misunderstand like this. Sir, omega is imaginary frequency. Omega is a real frequency. Yes, now the confusion started in your mind. I'm not saying omega is the real part. Omega is the really existing frequency. I'll write here. Omega is real frequency. Yes, it is really existing frequency. What are the units? Radians per second. Sigma is real part of the frequency. Real part of the complex frequency, but not it is the real frequency. Frequency means what? Number of cycles per second. See, as far as we learn, frequency means number of cycles per second. But what sigma represents? What is the significance of sigma? We are going to see. Omega will use in radians per second. If you convert into frequency f, you are going to get number of cycles per second. Means really how many cycles we are getting per second will be given by omega. That's why it is called as a real frequency. But unfortunately or fortunately, it is the imaginary part. Okay. Please do not misunderstand the statements. Definitely important for interview questions. If you go for research centers like ISRO, DRDO, definitely questions will be asked from this area. If you are choosing control systems domain or electronics domain, okay, mostly. Or if you take power electronics, also this for electrical students. If you are choosing power electronics as your specialization for M.Tech, then definitely these questions will be asked. Come on here. Omega is the realistic frequency. Really it is a frequency, but unfortunately or fortunately it is the imaginary part. Sigma is the real part of the frequency. What sigma represents? What are the units of sigma? Nepers per second. Electrical people will understand what is the significance of sigma more clearly in transmission lines. Even EC people are also having transmission lines and waveguides. There you will understand the significance of sigma. Please understand any concept completely in depth. Therefore, you can crack any examination. Okay, you need not to prepare for the second time. Come on here. What is the significance of sigma? If you observe, if I take an example, V of t is equal to some e power minus 2t into sine 3t. I'll take. Now let me draw its graph once again. What is the graph of sine 3t? I am drawing the graph of sine 3t alone. Sine 3t will be like this. Into what is the graph of this e power minus 2t? E power minus 2t graph is this one. Yes or no? This is decreasing. This is oscillating. Positive oscillation. Negative oscillation means negative side decreasing. What is the resultant graph? Let's draw the resultant graph. V of t is equal to e power minus 2t into sine 3t we taken. If we draw the resultant graph, yes, it will be like this. I told you, exponentially decaying sinusoidal waveform. What it is, ma? Exponentially decaying sinusoidal waveform. Yes, it is exponentially decaying sinusoidal waveform. Come on, let me draw. Yes, exponentially decreasing sinusoidal waveform this is. Okay. Who is responsible for this exponential decrement? This e power minus 2t is responsible for this exponential decrement. Means sigma is the one which describes about the decrement of the signal or increment of the signal. Suppose if I say e power 2t into sine 3t, it is increasing exponentially. That increasing exponential envelope will be given by this value of sigma. Be given by the value of sigma. Sigma is not really a frequency. It is not giving any number of cycles per second. That's why it is called as Nepper frequency. What does it mean by Nepper frequency? See, this wave is decreasing, but that wave is decreasing in a repetitive manner. That repetition will be given, or how that wave is decreasing in its magnitude, or how that wave is increasing in its magnitude will be given by sigma. As that is also happening continuously, to represent that one, we taken sigma, and we call sigma as also frequency. Sigma is called as what? Nepper frequency in radians in Neppers per second. Omega is called as what? Angular frequency or real frequency, realistic frequency in radians per second. So this is about complex frequency. Now let's list out all our what you call conclusions. Conclusions. I'm writing the conclusions here. Observe here. Note that is first point. S is equal to sigma plus j omega. First point. S is equal to 0 for DC analysis. For DC analysis. Come on, for DC analysis. S is equal to j omega for sinusoidal AC analysis. AC analysis. Or frequency response analysis, I call frequency response analysis. S is equal to sigma if the input is exponential. If the input is sigma means what? Omega equal to 0 if the input is what? Exponential. If the input is exponential. S is equal to sigma plus j omega, both will be there if the given signal is either sinusoidally, if it is exponentially decreasing sinusoidal waveform or exponentially increasing sinusoidal waveform. So with this we are done with complete Laplace transforms, means time domain to frequency domain, frequency domain to time domain. Many points we learn, types of signals existing there, Laplace transforms, inverse Laplace transforms, all possible theorems. We are least bothered about scaling factors, or not a scaling property f of at, that is you learned in your what do you call signals and systems in Laplace transform. There you are going to learn. We don't want scaling and all those things. Here we need shifting, time and frequency, initial value theorem, final value theorem, differentiation and integration, and all the basics that are required for control systems we are done with. So after this we are going to enter into system definition. With this we are done with signals and systems basics required for us. Now actual control systems will start from the next session onwards. In the upcoming discussion we are going to take up the definition of system. After definition of system, control system, classification of control systems. After that the transfer function, poles, zeros, physical significance of poles and zeros. See, if you ask anyone what is a pole, they'll say that denominator equation roots are called as poles, numerator equation roots are zeros. We are going to understand physically what does it mean by poles and zeros. Okay, so please, if you have any doubt, please get back to me. You have the numbers of faculties, and we have a dedicated Telegram group. If you have any doubt to post, please get back to us. Please revise all these things and come to the next class. Thank you.